Okay, section 6.1. We're looking for area between curves. I'm going to just do some examples that, just a few examples, that's all. So the first example I'm going to do is I'm going to look for the area between y equal 1 plus root x and y equal 3 plus x over 3. So the first thing to notice is that this is just a transformation of the square root function. And this is just a line, right? This is just the line 1 plus 1/3 x. And so I want to sketch the graphs really quickly. First thing it might help to do is just find the points of intersection. So points of intersection, I'm just going to set these equal to each other and see where they intersect. So here I can cancel those. I get root x is equal to 1/3 x. 3 root x is equal to x. 3x is equal to x squared. X squared minus 3x is equal to 0. Or sorry, this should be, if I square both sides, I get 9x here. And then I have x times x minus 9 is equal to 0. And then I'm going to go back and just make sure these actually are solutions because I squared both sides of the equation. And I can see that when x is 0, I get a solution. When x is 9, I also get a solution. So these are going to be the x coordinates of the points of intersection. So the points of intersection will be 0, 1. So I get the 1 by plugging into either of these. The other point of intersection is going to be 9, and I'm going to plug 9 into this guy, 4. Okay, so let's take a quick look at the sketch of the graphs. Okay, so I'm going to sketch the line first. The line has y-intercept 1, and it has slope 1/3. So if I go up 1, 1, 2, 3, 4, the line looks something like this. This is y equal 3 plus x over 3. And let's now sketch the transformation of this guy. So I have, I go up 1 unit here, and the square root function looks something like this. And then we know it has to go through this point. So it looks something like that. So we're interested in this area right here. And a typical approximating rectangle is going to look something like this. So I'm going to be adding up the areas of these rectangles and taking the limit as delta x goes to 0. Okay, so the key though is that I'm going to, in order to figure out the height of the rectangle, I need to subtract the bottom function from the top function. In this case, the top function I can see is this function, and the bottom function is the line. Okay, and so doing that subtraction will give me the positive height. So let's just set this up. So the area between the curves is going to be given by, this is sort of my formula, top function minus bottom function if I'm integrating with respect to x. So in this case, I'm integrating with respect to x. My bounds of integration are 9 to 0. My top function is 1 plus root x. My bottom function is my line, 3 plus x over 3 dx. Okay, and then let's just finish off this integration. I simplify a little bit and I get root x minus 1/3 x dx. So integrating gives me, that's the integral of this guy, antiderivative of this guy, minus x squared over 6. And I need to evaluate at 9 and 0, so I'm using the fundamental theorem of calculus. And I get 54 over 3 minus 27 over 2, which gives me 9/2. And sorry, I skipped a bunch of steps in between here and here. Okay, that's the first example. But I want to do another example where we're integrating with respect to y. So I want to find the area between the curves. Area enclosed between these two curves. Now notice the first thing is that these are functions of y, not functions of x. So they are functions, but the independent variable would be y. So these, also notice that these are both parabolas. They're sideways parabolas. So this is a parabola that opens right. And the reason I know it opens right is because the coefficient of the quadratic term is positive. This is going to be a parabola that opens left. Okay, so first I'm going to find the points of intersection just to help me with the sketch. One other thing I want to say is you can also see that the when if x will be 0 if y is equal to 0 or 2. And then here you'll see, so those are going to give me my y-intercepts. And my y-intercepts here are going to be, again, 0 and 4. Okay. So those are my y-intercepts. But let's find the points of intersection. So I'm going to just set these equal to each other. So I'm going to solve the system of equations. And let's see. So if I add y squared to both sides, I get 2y squared. And if I add 4y to both sides, I get 6y. So this is y squared is equal to 3y. Y squared minus 3y gives me 0. So at 0 and 3, I'm going to have points of intersection. So I'm just going to go back and figure out, well, what was the x coordinate? If y is 0, x is 0. So that's one of my points of intersection. If y is 3, using either of these, I'm going to get 3 squared minus 4 times 3. So 9 minus 12 gives me negative 3. So my other point of intersection is going to be negative 3. 3. So remember, this is the y coordinate. This is the x coordinate. So I'm going to use this and try to do a quick sketch so you know what the picture looks like. Okay, so first, let's start off by just plotting those points of intersection. 0, 0, and 1, 2, negative 3, 3. Okay, so my both parabolas have to go through those points. Let's now graph the first parabola, y squared minus 4y. This is the parabola that opens right and goes through y equals 0 and 4. Okay, so this guy is going to look something like, let me see, he's going to look something like this. This would be y squared minus 4y is equal to x. The other parabola opens left, and it goes through 0 and 2. But it's also got to go through these points. So let's draw that parabola. So it's going to look something like this. And this is, oops, sorry. This is the parabola x equal to y minus y squared. So that's my picture, and the region I'm interested in is this region right here. Now, a typical approximating rectangle looks like this. Okay, since these are functions of y, I am going to integrate with respect to y. And in this case, the area is going to be given by the integral. So these should be on the y-axis, the bounds of integration, since we're going to be integrating with respect to y. And I'm going to have, to get a positive height, I need to take the right minus the left and integrate with respect to y. So here I have the right function minus the left function. If I do it the other way, I'm going to get a negative number for the height of the rectangle. Okay, so my upper bound of integration appears to be 3. My lower bound of integration is going to be, so this is my upper bound. My lower bound is 0. That's where the rectangles end. My right function is the left parabola. And my left function is the parabola that opens upward, or right direction. So this is my integral. And if I simplify this a little, I get negative 2y squared plus 6y dy. There you go here. Remove my coffee. And I end up with a negative 2y cubed over 3 plus 3y squared. We're going to evaluate that at 3 and then subtract the evaluated expression at 0. This gives me negative 18 plus 27 minus 0 plus 0, which is equal to 9 is my final answer. Okay, so that's just an example of integrating with respect to y instead of x, and you might want to do that if you have functions of y as opposed to functions of x. In a lot of cases, though, you do have a choice.